Hello, everyone. Today we are hosting Professor Maher Al-Greer. He's visiting us today from Teesside University in the United Kingdom. Maher Al-Greer received his bachelor's degree in EE and MSc degree in computer engineering from the University of Mosul, Iraq in 1999 and 2005 respectively, and a PhD degree in electrical and electronics engineering from Newcastle University in the UK. In 2016, he joined the Electrical Power Research Group as a research associate at Newcastle and worked on Town and Country Hybrid Powertrain Innovate UK projects. He joined Teesside University in 2017 as a lecturer. Currently, he's a senior lecturer in electrical power engineering at the School of Computing, Engineering and Digital Technologies. His main research interests include battery systems management and control, signal processing, AIs, and machine learning in condition monitoring and control, digital power control and adaptive control technologies for power applications, diagnosis and monitoring, smart energy systems, and energy management. Currently, he is an associate editor of IET Power Electronics Journal, guest member of staff in the School of Electrical Engineering at Newcastle University, co-chair of Smart Energy Management, Conversion and Control Research Group at Teesside University. In 2019, he received the University Star Award for research performance. So thank you for accepting our invitation to talk today. I will let speaker continue.
Thank you very much. Thanks for this introduction. So I'm not going to add anything about the introduction. I'll go just directly with the presentation or the talk of today. So today I'm going to talk about system identification techniques in digital control design for DC-to-DC switch mode power converters. So first of all, we'll start with give just very brief introduction about the control methods that use for DC-to-DC power converters. And before we start that, just let me define, if you like, the DC-to-DC converters. So this DC converter is a circuit or device that used to convert or transfer the input voltage from DC form to another DC form. And the aim of that converters or any power electronic converters is to achieve high power efficiency, and ideally this should be equal to 100%, which means that the input power should be equal to the or ideally equal to the output power. The talk here today about the system identification and digital control or system or adaptive control techniques. I'm just focusing on the switch mode power converters or DC-to-DC switch mode power converters. And however, most of the techniques can be applied to other type of power topologies. And these DC converters have been used in many applications. And this actually slide here just to show one of that applications, which is the smart phone block diagrams. And if we look to that block diagrams, we can see similar DC to DC converters, such as step down or step up or step up down converters used in this block diagram. So the aim actually in this talk and the aim of this research is how to design an efficient control techniques that can produce a highly performance dynamic system using adaptive and system identification algorithms. Again, this is not applied to particular application, but can be used to different application from low power application to high power application system. Before we start looking at the advanced techniques that have been used, and I'm going to actually show you some of the state-of-the-art methods that implemented for this particular circuits or this particular converters. Let's look first of all, just to remind you about some types of those power converters. So there are different topologies of these DC converters, and I'm going to just look at the main power converters that usually used using the conventional circuits or topology. So the first one, which is the buck converter circuit, you can see this is a very simple circuit, and switch mode, which means that we are using one or two or maybe more power devices, such as IGBT, MOSFET, or silicon carbide devices, which is currently, or wide bandgap device that was currently used in many of the power conversion system. So the circuit here, which is known as buck converter or step-down converter, and the main aim in the control design is to find the model of that converter. So the mathematical representation, if you like, of that system. And because we have this switch here into the circuits, so which means that we have two states of operation. The first state, which is the on time, and the second state, which is the off time. And at each state, we will have different circuits topology or connection, if you like, into the system. And by using the differential equation, we can define or represent that circuit mathematically at the on time and at the off time. I'll show you later why we need actually to find this representation, but we need to keep in your mind that we need that because we need the model of the system to design the control or the closed loop control system. In a similar way, if we look at the other type of the converter, which is the boost converter here, this is the circuit topology of this converter. And again, we have one power switch here is used in this circuits. And we need as well to find the mathematical representation of that system at the two states, which is on time and off time, by using the differential equations. And after we use those or find those mathematical representation, we can actually define the state space model of that system, which is one representing the off time and one represent the on time of the system. And this actually apply for both of them. And as you can see, at the on time, we have these two matrices, and at the off time as well, we have those two matrices into the system. After we find the steady space model and to find the transfer function of that model, we need to actually to linearize those systems around the final points. And from that, we can actually drive the transfer function of the system, which define the transfer function between 2 points. And here, because we are looking at the control design, so we mainly look at the transfer function between the duty cycle and the voltage or output voltage of the system. However, we can actually drive any transfer function. For example, we can drive the transfer function between the input, which is the reference value, if you like, or the voltage input and the voltage output. But because of the control, we are mainly looking at or focusing on the transfer function between the duty cycle and the output voltage. If we design the voltage control mode control system. So this is the general block diagram of any closed loop system. And after we find the transfer function of the model or of the converter, we can actually close the loop and design the controller of that system. So we have two type of controllers. One, which is the voltage mode control system. And here I'm just looking at the conventional techniques using analog circuits to design that controllers. So into the using the voltage control, we can see that we have the feedback signals comes from the output, and we have the controllers here into the loop. So we have only one control loop into that system to control the operation of these switches to produce the duty cycles that make that system or that DC-DC converter regulated. In current mode control, as you can see, we have two feedback signals. One comes from the output voltage and one comes from the inductor current. So we have two control loop here, as you can see for that system, again, to generate the duty cycle or control the state of the switches, again, to produce the efficient or performance of the DC to DC or regulated output voltage for this DC to DC converters. So there are different techniques actually we can use in this control system or that control system. And I'll start with the simple one, which is just by using what is known as on-off controllers. So this is the characteristics of the on-off control system, which is mainly based on the error signal. And the error signal, which I should mention that, is defined as the differences between the reference or desired signals and the feedback signal. Again, I'm talking about voltage mode control methods, which is this block diagram here. So the control output is mainly depend on the sign of the error signals, which is the differences between the desired and the output voltage. And based on that sign, I can generate the control action. I'm not going to run the MATLAB Simulink, but I just want to mention that all of these actually can be built by using MATLAB Simulink, which is all of those components are available in MATLAB to build the circuits, and simply can test that control system and see the output response. So here we have implemented the system or the circuit simply for the buck converter in this example using the on-off controller. The interesting part is just to show the characteristics of this on-off controller. And as you can see here, we have two signals, one for the output voltage and one for the inductor current. And we have some kind of oscillation. Maybe if I'll just zoom out, I'll go to the next slide to look at the ripple value of the inductor currents. You can see we have a high value of ripple into the output current of the or inductor currents of that converters using on-off control. And this is not acceptable in this design because we don't have actually the controller doesn't have the role to control that ripple value. There's no control design criteria, if you like, or specification that we can include into the design of this on-off controller. So it's just based on the sign of the signal, if it is positive or if it is negative. And that's actually leads to that the duty cycle as well will be generated based on that changes between the positive and negative using on-off controller. So for this reason, we can actually go to the second one or the second type of the controller, which is the hysteresis controller, and which is some kind of nonlinear control system, if you like, using this hysteresis controller. And again, we can implement that using MATLAB, and simply we can use the relay block into the MATLAB to look at this hysteresis controller. And the interesting part here actually to define the hysteresis band into the controller, which has a main role into the ripple output, if you like, or dynamic characteristics of this control system. So again, you can see that here we have captured the inductor currents for two hysteresis bands, and here epsilon is, we select that between ±1, and we reduce that to -0.01, and you can see that this is playing an important role to define the ripple values of the inductor currents. Again, the only specification actually we can define here is the epsilon value. So we don't have another desired control specification. When I said the specification, if we design the control at time domain, so we have different type of a specification, for example, time settling, time rise, overshoot, you know, all of those time specification that we can define. We can do that using these types of control system. However, the implementation and the design of the controller, as you can see, is very actually simple to get a regulated output voltage using these kind of techniques. Very simple. So in the industry, which is well known that PID control system is mostly used. According to the statistic, 90% of the control system, maybe more, that using PID control system into different application, and switch mode power supply is one of those applications. And here is the general form or transfer function, if you like, for the PID controllers, which has three types of gains: proportional gains, derivative gain, and integral gain. And each one of those gains, it has different characteristics to control or to produce the desired performance or response into the system. So for example, you can see from that table, if you just select KP as a main control system into the loop or into the closed loop, so that will increase the overshoot. Settling time will be small change, rise time will be decrease, and error will be decrease. So let me show you some of those outputs using this type of controller. So in this block diagram here, or in this circuits, we just select actually, a PID controller, and here we're using a current mode control system. So you can see that we have the feedback as a current, and we have the feedback here as a voltage. So we have two proportional control, if you like, into the system, and we can see this is the response of that system. So that's using the KP. And if we can actually improve the response of the system, however, by increasing the value of the KP, but this can lead to unstable the system or instability of that system. So we can't just increase the value of KP to achieve the good performance. So for that reason, if we want to improve the steady state error here, as you can see, there is differences between the desired value and the output value. We can use a PI control system, which has the characteristics to improve the steady state error. And that's actually clearly shown in this performance into the system, but still we have oscillation into that system using PI controller. So if we want, actually here we use trial and error to find those gains and get that response. However, if we want to do that mathematically or using or following a steps or procedure to design that, there are different techniques to do that. And these techniques can be using body plots, root locus, or any other advanced control methods to find the optimum values of those gains to produce the optimum performance. And again, based on the desired specification in time domain or any frequency domain, if we are using the body plot, we can find the optimum gains for these desired specification to obtain the performance or the regulated output voltage. So actually, this may be well known to you, but I just want to show you the differences between the conventional techniques before we go to the advanced techniques using adaptive and self-tuning controllers, as well as to show you that what we are just producing here is all analog control methods using PID or hysteresis or on-off control system. So that's what, in summary, what we have look at in this particular part. Let me show you the differences between the digital control and system identification for DCtoDC converters and compare that with the conventional techniques. So before we look at that, there are different questions that why we use a digital control into the switch mode power supply. And first of all, when we developed or designed digital controllers, we can simply implement that into the microprocessor or microcontroller for real-time implementation, for online and real-time implementation of the system. The other points, which is very important, that we can actually reduce the number of components that we can use. We don't need those differential amplifiers, integrals, derivative, or other types of components. Using the digital control is all simply can be implemented by simple codes into the digital control design. Also, which is very important in power electronic applications, that it is low sensitive to the external disturbances. So we'll look at that when we see some parameter variation. Digital control is less sensitive than the analog controllers. Aging as well, component tolerance, all of that actually will be eliminated by using digital control system. So this is the block diagram of digital control system. Here we can see that we should have in digital control system an analog to digital controller and digital to analog controllers as well. And the aim here is to convert the analog voltage to discrete signal, because we have like a mixed system here. Some of the systems or components is analog, and thus, for example, the DCDC converters, maybe you need some kind of sensors and condition monitoring, and we need to convert that signal to a digital, then feed that signals to the microprocessor or to the digital control system to generate the duty cycle or the control actions that feed to the digital pulse width modulation. So the controller here will be a digital control, and the pulse width modulation here will be a digital pulse width modulation, which is equivalent to digital to analog converters. And the analog parts will be the DC converters here. So again, in MATLAB, actually, we can implement these analog digital converters. This is just simple block diagrams to show how we can implement that using quantizers, zero order hold, and some kind of delay that's representing the digital execution time and propagation. So to design the digital converters, we need actually to transfer this analog controllers. So there are two methods of the design of digital controllers: direct methods and indirect methods. The direct methods, that everything will be designed using digital system. And indirect methods is to convert the analog system from digital to analog conversion. So here we will design the PID control using continuous time domain, and we transfer that to the digital time domain. So we have all the values of the gains in digital domain, and we just implement it as a digital control system. And to transfer that, there are different methods actually, as you can see here. And each method, it has different characteristics based on the application that you are using the DC converters. So choose or the select between those methods is based on your system that you are going to design, and to be more precise is about the dynamic characteristics that you want in your system design. For the pulse width modulation, you can see it is actually similar to the digital to analog conversion. So we need actually just quantizers here to convert the signal to digital pulse modulation signal. So the first step then is, again, because we are looking at indirect methods, is to find the steady space model and then transfer that model to find the average modeling. And from the average modeling, we can find the transfer function of the system. And if we find the transfer function, actually, we can convert that system from analog to digital to find the digital transfer function, again, between here for this voltage control system between the duty cycle to output voltage. So if we do that and using the desired specification that we have put either in time domain or frequency domain, we can find the continuous PID controller and convert that to digital PID controller into the loop with the digital pulse width modulation and analog to digital converters, and we can actually get the output performance. And here you can see this is the output performance for this particular reference values with some load or rapid load changes into the system. So we see some overshoot and undershoot into the system, and we'll see how to actually improve that using more advanced control techniques methods. So the reason actually to use or to look at adaptive and self-tuning control schemes is to provide more efficient and accurate system that can track any changes into the system. We have to keep in our mind that all of the design here is based on the desired specification and fixed, which means that fixed values of PID gains based on the model of the system. So any change into the system or any aging or uncertainty will not be considered once we find the values of these gains. So for one of the reasons that we move to adaptive and self-tuning control scheme, actually, sorry, to track that changes into the system, which is in this example, or in this talk, is the DC-to-DC converter. So most of those adaptive and self-tuning controller, they need some sort of system identification algorithms to actually keep looking or tracking the input and output voltage to this system, and to identify that changes and feed that to the control system to tune their control parameters that will improve or mitigate that changes into the system. Let me show you one of the real advantages, if you like, for this self-tuning control that we have designed into the system. And here we have a DC-to-DC converters implemented using some kind of self-tuning controller implemented into the DSP. And you can see that the output of the DC is regulated now. And we will have some change or rapid change into the system. And in this example, we get a load change. And if you look at this, you can see that the performance now starts to improve because the controllers start to learn about this change into the system. That's actually output is an efficient response because we can see that they mitigate that changes. If we eliminate the self-tuning controller, you can see the changes is appeared. And now with the self-tuning, we don't need to learn again because the controller is already learned about that and produce an efficient output response. So the controller is already learned about this changes into the system. So you can see that how important is that. And now if we do the changes again, the self-tuning, it doesn't need to learn about these changes. They directly produce the efficient output response using self-tuning control techniques. So why we are using self-tuning controllers for switch mode power converters in general, and this is actually power electronic converters are nonlinear, and also there are certain types of uncertainties into the switch mode power converters or power converters, power electronics in general, which is component tolerance, unpredictable load changes, changes in the ambient condition, unexpected disturbance, poor knowledge of the load characteristics. We don't know what is we don't have knowledge about the load characteristics, aging effects, so fixed loop control gains, unable to consider all of these changes into the system. And that's why we need self-tuning and adaptive control system. However, most of these adaptive and control system required heavy computational complexity and sometimes not applicable for some high frequency applications. And that's why we need to look at the research more and try to develop an efficient algorithms or efficient adaptive techniques that can be implemented in real time and in high frequency application system. Actually, this is not just a research-based methods, and you can see here this is some of the off-the-shelf chips, if you like, or microprocessors that doing adaptive control and self-tuning methods for switch mode power supplies, in particular for point of load power converters. And each of those, they implemented different techniques of adaptive auto-tuning controllers system. However, there are many challenges actually into design adaptive control for point of load power converters. And one of the challenges that I just mentioned, which is the computational complexity, applicability to work in real time and in online manner, as well as accurate estimation of the system. And offline and online is very important as well to select between these algorithms. So this is the generic block diagram for adaptive and self-tuning control system using system identification techniques. And you can see it is similar block diagram to any digital control system. The exception here that we have a system identification that keep actually feeding that block with the input and output signal to find the model or to monitor any changes into the system, and feed that information to the controller to tune their parameters to generate the according control actions and or duty cycle signal for the DCtoDC converters. But if you can see here, this red block here, we usually need actually some sort of excitation signals for those system identification algorithms. And the reason for that actually is to increase the convergence time, and as well as to find the accurate parameters. And in power electronics or in switch mode power supply, pseudo-random binary signal or digital noise, digital white noise, if you like, is the most used in system identification, again, because of the simplicity of implementation of that type of noise into the system to excite this system identification and to produce, sorry, an accurate parameters. So accurate model is required to achieve a high performance control. This is what I can say why we need the system identification into the system. So we have, or there are actually two methods for system identification, and each one, it has advantages and disadvantages. So the first one, which is the non-parametric system identification scheme. And here, we don't need to identify the parameters of the system, but we'll identify the characteristics or the overall characteristics of the system. And body plot, for example, is one of the simple description, if you like, of this non-parametric methods. So this flow chart is show the steps or procedure that we need to follow to find or to identify the non-parametric system identification. Again, I'm going to apply that to switch mode power supply. So usually the switch mode power supply is working normally, and at the steady state period, as you can see here, the noise will be injected to excite the system, and we collect the input and output data. And by doing some pre-processing, for example, filtering, we can actually apply some kind of time domain analysis to identify the time domain response. And also, we can actually convert that to frequency domain response, again, using, for example, body plot techniques to find these characteristics. And from these characteristics, actually, we can find some parameters, or we can actually know what is the new model or new changes into the system. And here, actually, to show that using pseudo-random binary signal into this system usually is used to look at the non-parametric system identification techniques. The important point here, we don't need the transfer function of the model. So you can see, we just need to collect the data after the excitation. And I don't need to know what is the structure of the model or of the switch mode power supply to look at that. So this is a very good point, an important point actually in system identification. But if we look at parametric system identification techniques, which means that we need to find the parameters of the system. And that means we need to know the structure and the transfer function of the system, so we can identify which parameters that we want to estimate, and then we can apply the system identification. So this block diagram is again a generic block diagram for parametric system identification. You can see here we have the unknown system, which can be represented by this transfer function. And we need to know the model of the system before we start the estimation. And then we can actually use any kind of signal processing or adaptive techniques to estimate the parameters until we ideally achieve that the error prediction is equal to 0, which is defined as the differences between the output or the real output and the estimated output. So when both are equal, which means that this model is equal to that one, which means that we identify the parameters accurately. So this flow chart shows again the steps of system identification using parametric techniques. And again, usually the switch mode power supply is working at normal operation. Then we inject the noise. Just as an example, I use that one here, but we can use different kind of noise. And then we collect the input and output data, and we do some pre-processing, but we need to actually find or define the model structure before we do that, apply system identification to validate the model or estimate the parameters. If the model is not validated, we need to change the model structures to make sure that the model is fit with this unknown system. So this is maybe can be considered as disadvantage of using this kind of techniques. Just very quickly to mention that we can actually test it or implement different techniques of system identification, again, by using MATLAB or using LabVIEW. MATLAB, they have a GUI that simply can actually capture those data and can do some kind of non-parametric and parametric system identification, and is similar in LabVIEW. So in this part, we have looked at system identification, digital control, adaptive control for switch mode power converters. Let's look at some unconventional self-tuning controller for DCtoDC converters. And some of those comes from the state of art or from the literature. And I'll show you what we have done as well here in terms of system identification for switch mode power supply. And the aim actually that I'm presenting those just to show you that some of the examples, but actually there's a lot of research is going on around this area for system identification, and they use different system identification and develop different adaptive control techniques for a switch mode power supply. And in this talk, I just look at the system identification techniques, but as you know now, the artificial intelligence, machine learning algorithms becomes the hot topics. So now there are recent research, they actually use these techniques into the control design and smart or advanced control design for switch mode power supply. And all of those techniques that I am presenting is actually published in high quality journals, such as IEEE transaction on power electronics. So the first structure here that you can look at, which is known as the Hysteresis black box scheme. So in this scheme, actually, again, we have a switch mode power supply, and we have the input and output signals. And as you can see, in this scheme, there are two actually processing or two methods or algorithms, if you like, that used to find the model of the system, but considering the nonlinear model. So you can see here that we have the duty cycles of the input goes through nonlinear functions that to link the relation between the nonlinear characteristics between the control actions and the output voltage. Then this output will be fed to a recursive methods to identify or to find the model of the system. So these methods, I'm not going actually to go through what is the advantage and disadvantage, but I want to mention that I have published a paper in 2019 in IEEE Transactional Power Electronics, which is a review paper, look at all of these techniques and explain those in more details with advantage and disadvantage. But I can say that in these techniques is actually applicable for offline system identification, which is not applicable for real time and online system identification methods. This is the other structures by using a special kind of AAR filter. And again, here we have the switch mode power supply. And this is actually the block diagram of this MC Bright module that identify the parameters. Actually, this methods and that methods, both of them are using parametric techniques. So they estimate the parameters of the system to design the control system and to monitor any changes into the switch mode power supply. And this method also is a parametric techniques, but in that method, the excitation signal is not using a white noise or pseudo-random binary signals. Actually, they excited the signal by step change into the duty cycle. So they change the duty cycle by step change, which is here, I think, 0.1. And that step change will actually excite the output signals and feed that to the AAR filter and to the estimation algorithm to estimate the parameter of the system. So this, again, in real time or in real application is not applicable, or maybe is difficult to change the duty cycles, which means that the regulated output will not be fixed during the identification. These two methods is also parametric techniques, and they use the characteristics of relay estimation schemes, actually by use the relay here as a main controller into the feedback signal. And again, there's some nonlinear characteristics here, but the aim here actually that this error signals goes through this relay controllers to generate some kind of oscillation to the system. And based off that oscillation, we can actually find the corner frequency and the quality factor of the converters. And those two parameters actually is very important into the design of the control system because it is related to the components of the converters. In this work, they follow the same procedure, but instead of using the relay functions here, or relay feedback, they use the conventional I compensator or I controller. And the I compensator here will amplify this signal or error signal and will produce what is called the limit cycle oscillation. And from the limit cycle oscillation that are produced because of this I controller, again, they can actually measure the corner frequency and the quality factor of the converters to identify those two parameters and then actually design the control system or monitor changes into the switch mode power converters. Both of them are simple to implement, can be used for real-time implementation, but they need actually to produce some kind of oscillation into the output regulated system. So you just imagine that your DC-to-DC converters, there is some oscillation for some time, which is the time of the oscillation that we can see here to identify the parameters or monitor the parameters in the system. So when there is abrupt change into the system, like load changes, that will be actually difficult to monitor using these two methods. If we look to this scheme here, which is non-parametric techniques, they use actually the correlation analysis, and then they use the discrete Fourier transfer to find the frequency response of the system. So at the steady state, they injected some kind of noise, which is, I think, a pseudo-random binary signal here, and they take the output signal, and by using the correlation analysis between the pseudo-random binary signal and the error, they can then find the transfer function between the input and output, and we can actually find the frequency response characteristics. This technique is efficient actually methods to look at the switch mode power converters, non-parametric methods, but again, it is an offline techniques that need to collect the input and output data, so it is not a recursive methods, if you like, in system identification. This is a similar procedure. I think now this is a tools that use in Texas Instruments. So you can find that into the DSP from Texas Instruments is available, that tool, which is known as, or they follow the same procedure of network analyzer scheme. And here they also use the non-parametric techniques, but instead of injecting a pseudo-random binary signal, they swept sinusoidal signals through the converter. And then they capture the signals after the after the swept that signal or the chirp signal, and apply the discrete Fourier transform to identify the body plot of the system. This is exactly similar procedure of network analyzer, but it is implemented in a digital form and in real-time implementation. All of these techniques, actually, they developed these methods further. And the development here, looking at two factors, computational complexity and accuracy of estimation. So again, you can see that in this techniques is a non-parametric techniques and parametrics actually. And again, they used the power spectrum density methods to identify the power spectrum density changes into the system, and by using dithering amplification, so they amplify that noise for excitation instead of using or injecting some kind of noise into the system. And based on this power spectrum density, they can estimate the parameters, which is again here, the coronary frequency and the frequency of the capacitor's parasitic values. So based on those two values, we can identify the parameters and we can tune the gain of the system. And again, you can see this is similar structure, if you like, but in this one, they use analog correlation. It's not a digital correlation. So they use analog correlation here to identify the impulse response into the system by injecting some PN sequence or PN generators. And then they feed that impulse response into the microprocessor to find and apply FFT to find the frequency response of the system. And in this one, actually, they use this to find the phase margin of the system, which has a link with the damping ratio, or which means the dynamic response of the switch mode power converters. Let me show you what we have done here. So in this block diagram that I have developed an adaptive parametric identification techniques using recursive least square methods. And this techniques is parametric methods. And here, actually, in terms of procedure for estimation, we follow the same procedure, which means that the DCtoDC converter is at regulated points, and at a steady state error, we injected a noise into the system, which is pseudo-random binary noise. We enable that. And then we apply recursive techniques, but it is not the recursive methods that, or the conventional recursive method that we use, because it is very highly computational complexity in these methods. So we developed what is known as DCD RLS algorithm, the continuous coordinate Dicet algorithms. This techniques actually is solving this linear equations for any recursive estimation. So there is no, it is known as free division multiplication methods. So there is no division and no multiplication in this techniques. So it is low computational complexity methods that we have developed here. So if you look to this equation here, at each iteration into the recursive techniques, we need actually to find the parameters. We need to take the inversion of this matrix and multiply it by this matrix here or by beta. So this is actually lead to numerical issues because of the fixed point implementation, and actually it is computational complexity. So by using the DCD algorithms, we can actually find the parameters of the system without inversion and without multiplication. So it is a multiplication-free, division-free techniques, and we can identify the parameters. Let me show you the implementation. We have tested that. I'll show you in practically and in simulation. So this is actually by using the simulated model, we implement this DCTC algorithm. I want to mention one point that this techniques, it has been used for some of the underwater communication application, but not in power electronics. So it has been developed for FAR filter that's usually used in the communication application system to represent the channel in the application. But in control system, once you transfer the system from analog to digital, you will have an AAR filter, okay? So here, actually, I have developed, or we have developed these techniques to be used in AAR filter. So you can see that we have two FAR filter here, one at the input and one at the output, and the one algorithm will estimate the parameters for those FAR filter. Later on, when we come to the implementation, we find some difficulties and in terms of the robustness in this. So we combine both of those filters in one matrix, and we estimate the parameters here. Again, if you want to see more details about this, you can look at my paper here. For these techniques, how we represent both in one AR filter and one matrix and with AR filter, and then we estimate the parameters. So you can see that at the simulation, this is the regulated output. We injected the signal, we captured the input and output signal of the system. This is the output and the input, and you can see we estimate the parameters. So if you compare between this calculated parameter, and this is the estimated parameters, we achieve a very high efficient parameter estimation techniques. And this is obvious into the error prediction. You can see that after the convergence time, the error is approximately equal to or close to 0. And this at the time of identification. As I mentioned, we implemented that in real time. And here you can see the experimental data and the experimental estimation. And we compare between the conventional recursive methods and our methods with the calculated parameters. And you can see again that the parameters are estimated accurately using these techniques and very close actually to the recursive least square, which is very expensive in terms of computation complexity. And we have validated our model because there are two types of AR filter, equation error and output error. And here we select the equation errors model, and just to make sure that the model that we have been selected is accurate, and that's actually clearly showing that is achieved or validate our model that we have been selected. Later on, we have developed these techniques further, and here we try actually to track the abrupt load changes into the system. So if there is like changes like the load change into the system, which is the typical in switch mode power supply, you know, that this rapid change will be happening in the system. So we actually integrated with these techniques what is called forgetting factor tracking or adaptive forgetting factor estimation. Forgetting factor is the parameters that used or very important actually in recursive least square techniques, because the convergence time is depend on that. So high value will increase the convergence rate, low value will decrease the convergence rate, but will produce more robust estimation or less chattering signals, if you like. So we generate some kind of rule-based techniques based on the error signals or the difference of error signals prediction error signals from the AR filter, and to track the value or to find the optimum value of the forgetting factor, to track these changes into the system when it happens during the estimation. Actually, it's still there are some computation complexity that we need to look at using system identification, and the frequency of this switch mode power supply is increasing because that will decrease the size of those power converters. So here we have developed another techniques that actually reduce the computation complexity to 50% by using a Kalman filter methods, but this is a special kind of Kalman filter, which is known as the max Kalman filter or partial update Kalman filter. Sorry, the idea of this techniques that we are not just in a brief, that we are not estimating all the parameters of the system. The parameters that less change into the system, we just not estimate those parameters. We estimate the parameters that they have the higher change into the system. So we have here some criteria to look at the parameters, because we have two parameters linked to the inputs and two parameters linked to the outputs. And based on this mini M-mini and M-max functions, which is based on the amplitude of those parameters, we can then see which parameters that we need to estimate. So you can see that we can feed those parameters that we found that mostly fixed, if you look here, when there is change into the system. So we just estimate half of those parameters. So for example, here we have 4 parameters, we estimated 2, so the computation complexity will reduce by 50.
Dr. Greer, actually, we are above our time limit for more than 11 minutes now. Would you be able to wrap up your talk?
Yeah. So, yeah, I'll go very quickly. So we estimate the parameters, then we feed that to the control system for adaptive control design. This block diagram is again for another application, same application, but actually we use the multi-rail power converters. And here we have developed techniques or using one algorithm to look at the parameters of those converters and to then feed that parameters to the PID control for adaptive estimation. You can actually find the paper that we have published, and this is not updated. We have a new IEEE circuit and systems papers on this topic. And this block diagram, which is the final one, that what the video that I have shown to you actually comes from this new techniques. This is not based on the real estimation of the using system identification, but actually we found that there is a relation between the PD controllers, or based on this previous literature, they found that there is a relation between the PD controller and between the one-step prediction error filter. So what we do here, we use the one-step prediction error filter as a PD controller, and we estimate by using the DCD algorithm, we can estimate those gains of the filters and then feed that and track any changes. And we use as well the integral controller just without any excitation signal to amplify the error signal as an excitation for this control system. And you can see in this response, the accuracy of estimation of these parameters, the KD and KP, if you like, or the W1, which is the filter parameters, and the gain of this system. And this compare between the method that we developed and the conventional PID control. So you can see here that they produce efficient response during the abrupt load changes, but here there is some oscillation and they cannot track any changes into the system. Okay, so thank you very much for listening. And sorry, maybe I'm over the time, but I thought that this will be for 1 hour presentation. Sorry about that.
No problem. Thank you again for visiting us. Are there any questions? Some people may be leaving for other classes because classes started at 40 past the hour. Are there any questions from the audience?
My apology. I thought that it is for 1 hour, the presentation.
I have to say a couple of words. I'm Ahmet Hava from previously Middle East Technical University, now Ishuk University. Nice presentation. One thing I would like to say, I see we have young audience here. We have done a lot of work on this area, and you see a lot of we see a lot of material in the presentation. It's amazing to see how much complexity you can bring to a circuit that involves only 4 components: a diode, a transistor, an inductor, and a capacitor make the converter. And a lot of math and a lot of things get involved in it. In many cases, the cost of this converter, all in all, should be less than a couple of dollars. How will you make it so intelligent and so cheap is a major challenge. So the people who do research in this area are quite under severe constraints in terms of making it practical. So no matter how much you do in theory, eventually you have to bring it down to something that is multiply and add 2 numbers in simple ways. So it goes as complex and it has to boil down to as simple. The other thing so it's a very nice presentation and interesting subject. But the other thing, my experience with the power converters is basically, yes, the load variation is important and it can be as steep as shown in here. But the source side can also be problematic in terms of, for example, it could include some small disturbance on it, some periodic or aperiodic signals. And those disturbances could affect the output in some strict regulation applications. One is that. The other is actually in the circuit, the inductor especially can be nonlinear in the sense that it could be made of material and structure such that it's made cost-effective, and that boils down to a highly nonlinear inductor that as the current goes from half to full rated, the inductor can change by large amount. And this is done intentionally to reduce the cost to make the inductor small, not something that you don't want. But in terms of controllability, in terms of control behavior, sometimes the order changes, sometimes the eigenvalues shift. So here, all the things that I have seen, I missed a couple of slides. I had to go back and forth in the backstage, but all I have seen was mainly load disturbance, basically response to load disturbances. So how about other disturbances? What's the controller's response or the self-tuning structure's response to other disturbances? Thank you very much.
Thank you. Thank you. Thank you very much for your comments. Actually, it is a very valuable comments and for your questions as well. Maybe regarding the cost, which is the point that I totally agree with you, that you know that now the microprocessor and microcontroller become very cheap and very advanced at the same time, which give us the applicability and simplicity to implement this or investigate this kind of techniques now. It's not like before a few years ago. So that's make the challenge of developing these advanced methods applicable these days. In terms of the uncertainties or considering different type of uncertainties, most of the work that have been presented here is looking at the point of load power converters and the main changes in the point of load power converters, which is the load changes. So that's why we try here just to look at, or maybe we just have looked at the load changes as the resistors. However, when you look at the parametrics, for example, methods, these parameters, you know, A, B, or any other type of parameters are lumped parameters, which including C, the other components, if you like, of the circuits. So these changes into the system can also be considered to estimate those parameters or identify that parameters. But if you are considering uncertainties like, you know, noise or disturbances, actually this has not been investigated here. However, the good point that the recursive techniques and estimation techniques becomes more excited and more rich in frequency and details, if you like, when there's some noise into the system. And that will help the algorithms to do the estimation, or the convergence rate will be increased. However, this should be considered into the model structure. And I have mentioned during the explaining the differences between non-parametric and parametric techniques that we need to select the right model to estimate the unknown system. So yeah, so this is maybe the weak points here in the parametric techniques. If there is any uncertainty or other disturbances, that should be included. And that's why there are different, I haven't go through that detail, there are different structures of modeling that can considering uncertainties into the system.
Okay,
yeah.
thank you.
Thank you very much.
Yeah, but let me make another point here on the cheap processors. Actually,
yeah.
the world is in an oscillating stage. 20 years ago, there was the DSPs were very, very expensive. The FPGAs non-existent.
Yeah.
Until 3-4 years ago, really everything has become dirt cheap in terms of the processor cost.
Yeah.
Today, the processors have basically have been experiencing very, very high spikes in terms of pricing because of the lack of the semiconductor availability. So
yeah.
what's happened today in the world of engineers and researchers, actually all the techniques they have learned to implement with high performance processors, now everybody's trying to find a simple way that they can use the lowest bit numbers and the slowest processor to do the job. So we are back to 40 years ago when I went and started working in motor drives company. One big guy, one famous guy working on motor control has been assigned a very tough task. An 8-bit processor with 80 or 40 megahertz speed was basically a processor that he had to use to control the speed of a motor. If he achieved that job, the volume of that business was extremely large, that he would save the company millions of dollars. So now we are into the same position where we have to use complex algorithms with the simplest processors to do the job. Yeah,
that's true. Yeah.
Maybe it will change in 2 years ago. We'll get basically spoiled again with a lot of resources. But right now, the picture has changed. Food is expensive and processors are also expensive. Thank you.
Thanks. Thank you very much.
Hocam sesiniz gelmiyor.
Oh, I thank our speaker again, and I thank everybody for attending. And I wish you a great rest of your day.
Thank you very much. And sorry again. Thank you. Thank you very much.
Bye-bye.